and so forth. So the thing is that that field, which was developed, many decades ago, and it seems like it reached some kind of impasse. I don't know of any analytic theories that really, but maybe it should be have you thought about how that affects these diagrams?
Yeah, so I think Dr. Cohen mentioned about the complexity for real system for the boundary conditions. Simply saying, sometimes I hate to say this, but we're proposing like a poor man's method. If you want quickly dirty get a phase diagram, string phase diagram, you can use this. But if you want to do a real serial prediction, you may want to go to like a phase field simulation to consider all of the electrostatics, mechanics, domain wall energy, and some geometry of the materials. Yeah. Okay. Thank you. You need these two mics. Yeah.
Yeah, one is for me. Okay. All right. Sound good? Everyone hear me okay? Okay. I'm trying to use my digital laser pointer. Looks about to get is one screen now? All right. Oh, one plug this one. I should play this back. Can you play this back? As we need this one. Yeah, play it in there. All right. My name is Zi-Kui Liu. It's my first conference at Ferroelectrics. If I make some glaring mistakes, just raise your hand. I hope I don't. Let's go back to the first slide. Okay, parameter-free prediction of phase transition in that tight net. I hope it's be general in all Ferroelectrics. My name is Zi-Kui Liu from Penn State. And everybody knows that you see this volume change, right? A volume is function of last part is a function of temperature. You get a CA ratio, and it becomes C1, becomes cubic. So you know that is tetragonal and cubic, right? As we all learned. And then of course you're going to simulate it. So you do that. That's Ron had this one in 1992. At that time, I got my PhD in Sweden. And it's very nice, different structures. You got this unstable in the middle, and the two sides are stable there. Okay. And then he made some more work, Ron's group, 2005, about the pressure effect. Okay. And then 2008, Ron had another paper. And this inspired me to go to visit him. So I visited Ron at that time, try to understand it, because I'm not a Ferroelectric guy. I'm a thermodynamic person. Okay. Okay, so that's very nice. And Ron just showed today that you got something even more, you got even high pressure, 100, was that 89 gigapascal? Yeah, okay, got different structure. But this is only 2025, right? You go even further, you get a new phenomenon. That's very interesting. Okay. And of course, then you see that you can simulate it, right? As the question asked, Ron was doing 0 Kelvin, so you're going to find a temperature. And Karen's work back in 1997, calculate temperature factor, CA ratio, as the lattice parameter, and so forth. And of course, 1997, you move further, you get this Hamiltonian. I think this Hamiltonian actually was, from 1997, and it predicted the phase transition to the MD simulations. You can see a transition is like around a little bit below 700 degree Kelvin. And then they made a very nice prediction. That's a beautiful graph to show this domain formation. Okay, that's very critical. So that means if you can simulate your structure, if you don't have domain energy in your model, you should look at this paper. That means you revise your model. Your model is not good enough. That's why if you cannot predict this one. All right, so what's next? So it's interesting that you put them together, you will see, the one more results, actually very, very nice work from Vanderbilt's group, calculate domain wall energy. As you can see that domain energy goes like, this is, let's see, this is a 90-degree domain wall, this is a 180 domain wall as function of when you go from one side to another side. Okay. And of course, there'll be more calculations in the literature, and also from Karen's 2013 paper shows that the free energy now, our energy, because the energy function temperature for 90 degrees is almost constant, for 180-degree decreases. Yeah, very nice. It's interesting that for the 90-degree domain, what the energy doesn't change much, the free energy. You can see about free energy from the MD simulations. Very nice work. So I call this work bottom up, right? Bottom up from the bottom all the way to predict. Of course, you realize that, right? You start from 0 Kelvin moving up there, you're going to be less accurate with a high temperature. So I thought it would be, what goes from top down? Like the previous boss talking, it's going from top down, right? You fit the parameter to this Landau equation, you predict it. That's completely top down. Can put them together. Okay? However, you want to put them together, you have to understand the experiment better. So what happens? I look at the experiment again. And turned out back in 1994, there's some experiment that says that. Okay, 1994 experiment says that actually, even though the X-ray shows this CA ratio equal to 1, but you look at the individual atoms, most of them do not go to CA ratio equal to 1. That means the atoms do not sit in the middle. They go away. They stay like CA ratio all the time, way above the transition temperature. That means you actually do not have cubic. You actually have orthotrigonal. And then, of course, the more experiment data, you have neutron scattering, and they show that if the X-ray and neutron, it goes down back to the kind of cubic. You don't see it. But if you look at the XRF, look at the titanium atoms, there's no tetragonal. Or most of them not tetragonal. Of course, what happens is that you have this kind of perturbation. Okay, so what happens here? We do some, that inspired us to do some AMD simulations. AMD, it's a initial molecular dynamics, there's no fit in there. So you can see that. So you fix this system at 753 Kelvin and cubic. The box is cubic. Okay, then you look at each atom. So what do you see that? The blue one is titanium. Blue one is titanium. And they don't stay at the center. At any moment, the titanium is going this way, that way, this. They fluctuate all the time, right? At the time. Of course, you look at even more, you can see, okay, how it looks like. You see the different atoms, sometimes this, and go like that, and go like this, right? So when these flippings take place, you will find the domain walls, local domain walls, right? If one doesn't move, one moves to 90 degree, you get 90 degree domain wall locally. The small ones, atomic scale domain walls. If you go to low temperature, you find that the flipping becomes less frequent. If you go to 0 Kelvin, of course, no flipping, right? You get a ground state. All right, so then we thought maybe we can do some work about this one. We do some statistical analysis. This red line is from the AID simulation. We take experimental lattice parameter, fix the CA ratio, we'll do simulation. We find that you have the CA ratio all the time. So you got the cubic all the way up there, okay? Way above to the transition temperature. And it's the shift between the XRF and the simulation because we take the experiment CA ratio. That's pretty nice. That's a very nice agreement, okay? Then you look at the polarization. Polarization, again, above the transition temperature, use X-ray and the neutron is 0 overall. But if the individual ones, the titanium is off, right? It's displaced. It's displaced. Yeah. So that means if you really want to model this one, you have to look at this kind of fluctuations. Of course, we know that how do you look at fluctuations? You look at the statistical mechanics. Okay, we know that a partition function of system is partition function different configurations. You get this standard one, and then you calculate the probability, then you calculate the energy, you calculate the entropy. Okay, that's your statistical mechanics. So what the problem with this one? Oh, no problem, of course, it works very nicely. How we imagine the system will have one configuration. What does that mean? That means F equal to E. If F equal to E, that means either T equal to 0 or S equal to 0, right? But we know if we go above the temperature, T is not equal to 0, S must be equal to 0. So if S equal to 0, we know that is called the pure quantum state, because that configuration has only one state. It doesn't have two states. 2 belong to 2. Okay, that means this theory applies to system with all the configurations are only pure quantum configurations. Well, that's what the quantum theory is about. That's what Landau derives the statistical mechanics for quantum system. But however, when you do DFT, the quantum state is not a pure quantum state, right? Because you increase temperature level, you got a phonon, you got all the vibrations. So that means this theory itself does not apply to DFT-based quantum mechanics. So we have to modify it. So how do we modify it? Look at the titanate, as we showed in the previous AMD simulations. The atom moves like this, look like that. So you create ferroelectric state. You create a 90-degree domain. You create a 180-degree domain walls. So I have only 3 structures. It's a ferroelectric structure, macro configuration, 90 domain, and 180 domain. And of course, you know, this is a system have been studied, as I showed before, it carries energy, right? But it's important, they are not a pure quantum state. So you cannot use their statistical mechanics from top down, put them together, but you can calculate energy. How do you calculate? You can phonon of them, right? You can do the electron contribution and the phonon contribution with the standard. Whether you can run a code, you can calculate them easily. Take a few seconds, a few minutes maybe. And unfortunately, in this paper, 2002 from Lanny group, they calculated energy. They didn't calculate energy. But energy turned out not too bad in this case. Okay, so what it means is that let's look at the missing part in the statistical mechanics just talking about. But the idea is that in the system, you can divide into different configurations. Each configuration has a probability to put them back. It gets entropy. Okay. But I just mentioned the DFT calculations give the configuration with entropy not equal to 0. So you have to add one top, right? You have to add one. That means each configuration has entropy. So that's simple, right? Just add those 2 together. So that's the entropy. Now entropy has one extra term, which is the summation of the contribution for all configurations. So still top down, but now we need to go one scale lower, right? One scale lower. So well, how to do that? We can do DFT calculation. All the way go down the electrons, go to quantum DFT, go to the ground state, non-ground state, calculate all of them, put them back. I call it the bottom-up contribution. So if you put a bottom-up, a bottom-up, top-down together, we call it entropy. Again, I want to discriminate that the name was not invented by me. I gave a talk in 2021, and somebody said we should call it entropy. I like it so much, so I used it. All right, I see. So basically, that you have the quantum and statistical, put them together. Okay, now you can predict. Then we believe we can predict what you can measure. Because what the experiment? The experiment you measure them, right? You sample different configurations, put them together. That's what the experiment does. So how do you get it? You do integration of heat capacity, T over T do integration from 0 Kelvin up for all the experiments. So we think we can predict it exactly as you would measure from experiments. That's called parameter free. So it means a quantum statistic and some of them put them together and you get free energy. Now is the big difference compared to the standard statistical mechanics that need to change the E to F. Okay. Because now each micro configuration has its own entropy. If the other one, we can predict many things. And we started this one with magnetic materials. The difference between the 2 is just whether SK equal to 0 or not. Okay, so equations are all same. All right, so we did magnetic calculations, and I don't have time to go through all of them, but just show you come flight. We predict transition temperature as good as experimental measurements. Okay, it's one system. We did another, and even more important, we predict negative thermal expansion in this temperature range, pressure range. So negative thermal expansion or negative ferroelectric effect is not intrinsically of the lattice. It's a mixture of different states that compete each other. It's a competition between different configurations. It's not intrinsic. Of course, if we compete together, reflex you can measure its softening model modes. All right, we did it for Syrian too. Syrian now the positive thermal expansion. You can see that. It's positive. It's something positive here, okay? Positive and negative both can be predicted. And even more important, we can predict the barrier from one side to another side. We can calculate the barrier between phase transformations, predict it again with this kind of combination. Now, my collaborator Alex Zonger is back there, and I want to thank him to give us a very challenging problem for the Nicolate a couple of years ago. It took us quite a few years to figure out how it works, but I want to tell you that our prediction is 144 degree, experiment is 145, without any feeding parameters, even no models. All right. So I have to go back to the titanium, right? The titanium will have 3 configurations. Turned out, as shown by Karin's MD simulation, entropy are very close. That means we don't need entropy in this case. So take Vanderbielt's free energy as energy at the domain was, we can actually calculate. We can then mathematically show that the entropy effect is very small if the entropies of different configurations are the same or similar. So we take that together. We just put it into our model. So I have 3 configurations now, right? So you have ground state, it's ferroelectric, which is at 0 Kelvin, 100%. And there's two domain wall structures at 0%. When temperature goes up, and you see the probability of the 90 degree, of course, increase a lot because that's much lower energy. 180 degree increase very, very little because energy is very high. There's red line down there as 180 degree, almost zero. Okay. So this one predicted the transition temperature 776 Kelvin. Again, no models, no feeding parameters, and the experiment is 763. That's not too bad because we take data from the literature, right? We haven't done any calculations ourselves. I met quite a few people here. Maybe we should work with you guys to do better calculations. And then if we take another data from the literature, it was different data, right? 29. It's just for another publications because this publication actually has some problem. The reason is because you relaxed everything. In the reality, the structure do not relax. Okay? You have to get it. Quasi-harmonic calculations. Anyway, it's not too bad, 645 degree from that data. Okay, now you can calculate the contribution from this kind of configuration. It's huge, okay? It's 1.5 kBT. It's huge amount. All right, so I do want to mention that my time is almost up. This talk about this negative or positive thing. You look at this matrix here. Matrix is between the conjugate variables between potentials and molar quantities, okay? If this matrix is symmetric based on Maxwell relation, the diagonal terms are always a positive. They can never become negative, unless the system is unstable. However, the off-diagonal terms that between the two non-conjugate variables, they can be positive or negative, because the natural laws do not require them to be negative or positive. You know, just like people, right? You don't give constraints, they do whatever they want. All right, but however, I do want to mention next table is called the derivative between two potentials that we're working on called the cross phenomena. Some electrochemical, electromechanical, and some of the electricity, some of the efficiency is all from this table. It's all from thermodynamics. You can calculate them and predict them and compare with experiment. All right, with I summarize that the entropy theory integrates the bottom up DFT and top down statistics together and can predict things. And without models and feeding parameters. But important, we have to replace the total energy by its free energy from the DFT calculations. And there are three key configurations for lead titanate: the ferroelectric state, the 90 domain wall structure, and the 180 domain structure. For different complex structure of barium titanate, you're going to have more domain structures. So just calculate by DFT, we put it back into it. And if you can predict it, we can predict the phase transfer, including the some experiment. I want to mention it's very important. When you put them back together, you have to have the same MVT for all configurations. In the classical way people do it, they get a minimum, local minimum, get the ground state. Or if relaxed, you will not get it right. All right, we're actually working on different things. We looking forward to work with the experts, you guys on the ferroelectrics. Again, I mentioned I'm not an expert on ferroelectrics, but I hope this method can be useful for you people. Thank you very much.
Questions? You get the relaxing model. I have two questions. If you don't know anything about the material a priori, if you don't know